This is a good point to introduce random walks. Random walks have many uses. They can be used to model random movements of molecules, but they can also be used to model spatial trajectories of people, the kind we might be able to measure using GPS or similar technologies. There are many different kinds of random walks, and properties of random walks are central to many areas in physics and mathematics. Let's look at a very basic type of random walk on the whiteboard. We're first going to set up a coordinate system. Let's call this axis y and this x. We'd like to have the random walk start from the origin. So this is position 1 for the random walk. To get the position of the random walker at time 1, we can pick a step size. In this case, I'm just going to randomly draw an arrow. And this gives us the location of the random walker at time 1. So this point here is time is equal to 0, and this point here corresponds to time equal to 1. We can take another step. Perhaps in this case we go down, say over here, and this is our location for the random walker at time t is equal to 2. This is the basic idea behind all random walks. You have some location at time t, and from that location you take a step in a random direction, and that generates your location at time t plus 1. Let's look at this a little bit more mathematically. First, we're going to start with the location of the random walk at time t is equal to 0. So position x at time t is equal to 0 is whatever the location of the random walker is at the beginning of the random walk. We're going to call that x naught. This is our step 0. The next step is going to be the location of the random walker at time t is equal to 1. This will be given to us by the location of the random walk at the previous time step, t is equal to 0, plus some displacement, delta x, at time t equal to 1. Because x at t naught is simply given by this term over here, we can simplify this to x naught plus delta x at time t equal to 1. Let's then look at the next step. The location of the random walker at time t is equal to 2. Again, the basic idea is the same. The new location is going to be the old location, meaning x at time t is equal to 1, plus some random displacement, delta x, at time t is equal to 2. Note that the index of the random displacement matches the index of time over here. From what we have above, we see that we have the location at time t equal to 1 here, which we know to be equal to this term over here. What that means, I can now rewrite this part as this expression here. So we have x naught plus delta x at time t equal to 1 plus delta x at t equal to 2. This term over here is just the same term that we had above here. All we've done is we've just copied that term over here. We can see that a common pattern starts to emerge. To know the location of the random walker at time 2, we had the initial location plus displacements at time t equal to 1 and t equal to 2. From this we can write down the general equation for the location of the random walk. We start with x at some point in time t is equal to k, for example. We will always have the initial location x naught, and this is going to be followed by a sum of displacements. The first displacement is going to be this term, delta x at time t equal to 1. This will be added to the displacement delta x at t equal to 2, all the way to displacement delta x that corresponds to t equal to k. In other words, the location of the random walker at any point in time is given by the initial location x naught plus a sum of all of the displacements from 1 to k. Let's review the logic of the argument here. First, we start at time t is equal to 0, which we decided we're going to call x0. Then at time t equals 1, we take the previous location that we had at time t equal to 0, and then we add a random displacement to that. That gives us location at time t is equal to 1. I'm going to use the blue color for this. Then when we look at the location of the random walk at time t is equal to 2, we take the location at t is equal to 1 as our starting point. Again, we add the random displacement. The final result is the following. To find out the location of the random walker at time t is equal to k, we take the initial location of the random walk, and to that we add a sequence of random displacements. If we're interested in the location after k steps, then we will have k such random displacements in the sum. We've just seen that the location of the random walker at any given time t is given by a cumulative sum of the previous t displacements leading up to that point. Let's try coding up random walker in NumPy, where we start at the origin, take 100 steps, and where each step is sampled from the standard normal distribution, the normal distribution having mean 0 and standard deviation equal to 1. We're also going to assume that the x displacement and the y displacement for any given step are independent, such that the displacement in the horizontal direction has nothing to do with the displacement in the vertical direction. We can start by generating the displacements. I'm again going to keep the numbers small and start with just 5 steps. Let's generate a 2x5 table of numbers where each element, each of the 10 numbers, is drawn independently from a standard normal distribution. To do this, we will use the np.random.normal function. In this case, we'll be typing np.random.normal. The first argument is the location or the mean. The second one is the standard deviation, which is 1. And we wanted to generate a 2x5 table, 2 rows and 5 columns. And we can try running this a couple of times to see that the dimension of the table matches what the expectation was. I'm going to call this table delta x because this encodes the displacements of the random walker. So delta x equals np.random.normal. Let's then plot these displacements. We can take the first component of each vector as the x-coordinate and the second component as the y-coordinate. We're going to be using plt-plot for this, so we'll say plt.plot. We'll be taking the delta x array. We would like to get row 0 from that array. That's our x component. And our y component, the second argument to the plot function, is going to be delta x1, which is row 1 of delta x. Then as the third argument, I can specify the color and marker. I like to be using green circles for this plot. And then we run the code. What is shown here are the displacements that we generated from the normal distribution. It may seem like we're just getting started with this example, but in fact we're almost done. The one missing piece that we need is what is called a cumulative sum. Let's first look at what that means. Let's have some numbers. 2, 4, 1, 3, and 2. Underneath, we'll write the cumulative sum. The first element is just going to be equal to 2, the first element here. The next element is going to be whatever we had here plus the element above. 2 plus 4 gives us 6. This element is going to be 6 plus 1, that's 7. 7 plus 3, that's 10. 10 plus 2, that's 12. But how can we do a cumulative sum in NumPy? Let's just Google that to find out. Cumulative sum in NumPy. In this case, the first hit gives us what we would like. NumPy has a function called cumulative sum, and it requires at least one argument. In this case, the function requires one compulsory argument, which is an array, in this case called a. The second argument, axis, which is optional, specifies the axis along which the cumulative sum will be computed. Let's practice the use of the cumulative sum. np dot cumulative sum. It's going to be applied to delta x, which is the first argument, and the second argument specifies the axis. We're going to be using axis equals 1 because we would like to take the cumulative sum over the columns of this array. I would like to store this result. I'm going to store that in x, this capital X. And if we look at the contents of the array, we'll see that we now have a cumulative sum taken over the columns. We can contrast this with delta x, which only gives us the increments that we sampled from the normal distribution. Let's now put the different pieces together. First, we generate the random displacements, np.random.normal, mean 0, standard deviation 1, and the size of the array is 2 by 5. This gives us our delta x, our random displacements. On the following line, we'd like to define x, which is the position of the random walker at any given time. So we apply the cumulative sum here, applied to delta x, and axis being set to 1. Finally, we want to plot this using PLT plot. First, we'll plot the row 0 of our x array, and then we plot row 1 of the array. Let's try running the code. Let's try making a small modification to the plot. I would like to be using red circular markers, and I'd like them to be connected with straight lines. I would then like to save this figure, so I'm going to be using the savefig command. And I'm just going to call this RW, short for random walk, and I'd like that to be a PDF file. I will then run the code, and let's look for the PDF file on my computer. This shows us the first 4 steps of the random walk. But there's one problem here. Remember how the random walk was supposed to start at the origin, at location 0, 0. Right now we're missing that very first point. But let's add that element to our array. In this case, the origin is represented by a 2 by 1 array consisting of zeros, and we'd like to concatenate that to our array called x. Let's again use Google to find out how to do that. How to concatenate NumPy arrays. Again, the first hit looks promising. In this case, we need to provide 2 arguments. The first argument is a tuple of the arrays that we would like to concatenate. The second argument, axis, is the axis along which the arrays will be joined. So the missing step for us to do is to generate the array x0, and we know that this is a NumPy array. It consists of 2 rows, each having just one element, 0. This array x0 gives us the initial location of the random walker. Let me take this line of code and move it to the top here in my window above, and we can now write the concatenation function. We start with np.concatenate, and we need to provide 2 arguments. First is a tuple of the arrays that we would like to concatenate, and the second argument, axis, specifies the dimension of concatenation. In this case, axis is going to be equal to 1. Let's now look at the tuple argument a little bit more carefully. The first array is going to be x0, the starting point of the random walk. For the second argument, we will need to insert our cumulative sum from above. So this is the cumulative sum applied over delta x along axis 1. This entire expression here will give us the location of the random walker, which is x, this time including the origin as the starting point of the walk. We can now inspect the array x, and we'll see that the first element is 0. We're now ready for our final solution. Let's first copy this bit of code from here. This replaces our previous definition of x. So we now define x naught. We generate our delta x's. We then define x, the location of the random walk, and we then make the plot. Finally, we'll save the figure. I'm going to save the figure now to a file called rw2, and we can run the code. Let's again look at the PDF version of the plot that we just generated. We're looking for rw2, and we can see that this time the random walk does start at the location 0, 0 at the bottom of the figure. Let's now run this 100 times. We're going to change the argument here that specifies how many random displacements I would like to generate from my random walker. I'm going to save this in file rw3, and then we'll run the code. We can look at the file, searching for rw3, and this is our random walker, which takes, in this case, 100 steps. To wrap this up, let's generate a couple of realizations of random walk taking 10,000 steps.